So the next step is to understand the method of Lagrange multipliers. So let me tell you what this method is. Here's a picture of Lagrange. The French took Lagrange for themselves. Lagrange was Giuseppe Lodovico Lagrangia, born in the Kingdom of Sardinia in Turin. So he's not quite French. So in any case, Lagrange came up with this method. That is a very interesting method. But let me tell you what are we trying to do. So I want to find, again, some extreme values of a function. But now I'm going to find them on a region, just sort of like what we were doing a moment ago that I did by trying to what we did previously in the previous section would have been, OK, try to solve for one variable and make this a one variable function. But instead, sometimes that is not possible. If this is some function that I cannot just like solve for one of the two variables, that doesn't always work. So here's what we want to do. So I have a circle of radius 1. Well, I have a function, f of xy, that is defined. The domain is all of the real plane. But I have a circle of radius 1. And again, I want to find what is the largest value of this function in this circle. So I don't know where the max is going to be, but I want to find those max and minimum values of that function just in this circle, not the filled-in circle, but just the circumference of this circle. So how are we going to do that? In general, what we are going to do is this method of Lagrange multipliers. So let me go back to, we're going to use the gradient vector, and we're going to use a property of the gradient vector, which is the following. Remember, when we looked at gradient vectors, we found that if I have a surface, like the graph of a function, but this graph of a function is a surface in 3 dimensions, this gradient vector, the derivative with respect to x of this f, derivative with respect to y, comma minus 1, is actually normal. It's perpendicular to the surface at any point. OK? So that tells me that if I have some, say, paraboloid, and you take a point here, then the vector is going to be normal to the surface. In this case, we're going to see that it points inwards, but it's perpendicular. And we use that vector, that's the vector we use to come up with the equation of a tangent plane. OK? And we saw that the gradient vector in 2 dimensions is normal to any level curve. So if I make a level curve that goes by that point, and I look at my level curve, and I look at the point here, this gradient is going to give me a normal vector, so a vector that is perpendicular to the tangent line to that cross section. OK? So this is going to be given by this one, and this is going to be given by that vector. So those vectors are very useful in coming up with tangent planes, with coming up with tangent directions, but also, more importantly, is that this gradient vector indicates the maximum rate of change of the function at that point. In the entire domain, at that point, the function is growing fastest in that direction that the gradient vector is pointing at. OK? How did Lagrange use this? Let's do some practice on finding those normal vectors so that you see just for review of this concept, let's find the normal vector to the graph of f of xy at 1, 1, 2. So first of all, I want to take some derivatives. The derivative is minus 2x. The derivative with respect to y is minus 2y. So part A is this gradient vector, which remember is f of x, f of y, minus 1. So in this case, this gradient vector is minus 2x minus 2y minus 1. And if we evaluate at 1, 1, 2, what do I get? I get minus 2, minus 2, minus 1. This, by the way, it is a hyperboloid. Okay? And at 1, 1, 2, let me do a better job. At 1, 1, 2 is here. And what this is saying is that the vector is minus 2, minus 2, minus 1. So it is pointing somewhere in that direction to the inside of the paraboloid. Right. Now, what is the tangent plane? The tangent plane, remember that is given by, the derivative. Let me write it with fx. At the point times x minus the x coordinate plus the derivative at the point times y minus the y coordinate plus or minus, in fact, z minus z0 equals 0. Okay? So the tangent plane will be, the derivative is minus 2, so it's minus 2 times x minus the coordinate is 1 plus also minus 2 times y minus 1 minus z minus 2. Okay? See that the coefficients that appear in the plane in front of the x, the y, and the z are precisely these coordinates. Minus 2, minus 2, minus 1 is minus 2, minus 2, minus 1. So this is the equation in point form of the tangent plane. And then let me see if I do have extra space here. So find the normal vector to the cross section z equals 0. First of all, what is the cross section? When z is 0, the cross section is x squared plus y squared equals 4. So the cross section is a circle of radius 2. Okay? And then I have one point, say a square root of 2, a square root of 2. So what is the normal vector will be given by the gradient, which is the derivative evaluated at that point. Okay? And that will be f of the first derivative, which is the first derivative of f here, minus 2x, minus 2y, evaluated at a square root of 2, a square root of 2, and that is minus 2, a square root of 2, minus 2, a square root of 2, which is a vector that is parallel to the diagonal, so it's some vector in that direction. What does it tell me that that vector points in that direction once I have a cross section? Remember that the direction tells me that the graph grows the fastest if I go in that direction. This point is in the diagonal, this vector points to the origin, so it's in the diagonal, it's in the direction of the origin. The growth of the graph is the largest. But remember that this graph is a paraboloid, and the tip is at 0, 0. So from here in this cross section at z equals 0, I do want to move in that direction to get to the largest possible value. Okay? And in any other direction, the graph would, for example, it would decrease the fastest in that direction. It would stay about the same if I go in one tangent direction to the circle. Okay? But the point is that this normal vector, it also gives me the fastest growth of the function at that point. In part A, this -1, that is part of the formula. So this was the formula for the normal vector in 3D. it came like this already, because what we saw previously is that, so the graph itself is a surface of the form f of x, y minus z equals 0. And the normal vector will be given by the three derivatives. It will be the derivative with respect to x of this. But this doesn't depend on x, so it's just the derivative of f with respect to x, comma, the derivative with respect to y. This doesn't depend on y, so it's just fy. And the derivative with respect to z, but this doesn't, it does not depend on z, and the derivative with respect to z here is a minus 1. So it's just the formula for the normal vector in 3 dimensions to come up with a tangent plane is given by this with a minus 1 at the end. When it's in 2 dimensions, it's just for cross sections. It's just the normal, this should be delta little f. It's just the gradient vector of little f. So then how are we going to use that to find solutions of these kind of equations? I want to maximize a function on some curve g given by gxy equals k. So here in blue is the graph of g, and the rest of the function is defined in the entire R2, say. Then what I want to know is how to find, so in here, if you see drawn in purple or in pink, are the level curves of the function f, and you can see that it looks like the maximum value, at least in the part of g that is pictured, is going to be right here. Here is going to be the max. How can I distinguish that point? For example, could it be that the maximum value is here or here? It cannot be, because if I compute a gradient vector, the gradient vector at that point, if you look at the level curve for f is equal to 7, look at that level curve. What will the gradient vector tell me? The gradient vector will tell me that it will have to be normal. It will have to be perpendicular to this cross section, to this level curve. So it has to be somewhere like that, more or less. Okay. So it's telling me that actually, if I keep moving on that direction on the curve g, the value of the function will increase. So I'm not at the maximum value. Could it be that the graph, it has its maximum value here? I look again at the normal, at the vector that gives me the growth, the maximum growth is in that direction. So it should be that if I keep moving in the blue curve in that direction, the value will increase a little bit more. However, at this point, the vector, the delta f, will be perpendicular to both this level curve and this curve. So it doesn't tell me that I can move any more in any direction on the curve g and increase the value of the function f. So if I move in this direction, I know that the value of the function is going to not increase because the largest increase is going in that direction. And in fact, if I go in this direction, I start to decrease value. If I come back in that direction, I start to decrease value. So the fact that the tangent line to the curve is normal to this direction vector that is given to me by the gradient vector tells me that I cannot grow in value anymore at that point. So that is exactly what the method of Lagrange multipliers tells you, is that the value on this curve where the maximum value will occur will happen when the gradient vector of f is parallel to the gradient vector to g. So if you compute both gradient vectors, they will be both parallel at that point. In this point, for example, the gradient vector for g goes in that direction, but the growth of f tells me keep going in that direction because you are not at the max. But when they both are parallel and pointing in the same direction, at those points, there will be either a maximum value or a minimum value for G. And that is exactly the method of Lagrange multipliers. We have to find for at what points the normal vector to the points on G and the normal vector for the level curves of F are parallel, given the constraint that they have to still be points on that curve given by G equals K. Again, this is the method. So let's find the extreme values of f of x y equals that function, and on the circle x squared plus y squared equals 1. Okay? So what I need is to set up, the equations like that. So I need to compute the gradient vector for f. Here, by the way, this is the graph g of xy equals 1. So g of xy is x squared plus y squared in this case. The gradient with respect to f will be the derivative of f with respect to x, which is 2x. The gradient with respect to, the derivative with respect to y is 4y. And then the gradient of g will be 2x. So now I have to see when are these two parallel, and at the same time they have to satisfy that equation. Okay? So this is the same as I want 2x 4y to be parallel to 2x 2y, and x squared plus y squared has to be 1. And this gives you two conditions, because the x coordinate has to be a multiple of the x coordinate here, and this coordinate has to be a multiple of that one. So this tells me that 2x is equal to x lambda, that 4y is equal to 2y lambda, and that x squared plus y squared equals 1. And you have to try to find all the possibilities, all the possible lambdas where this might happen, all the possible x and y's where this might happen. All three at the same time have to happen. All right, so the first equation, if I bring everything to the left-hand side in this case, is 2x minus 2x lambda. So I'm going to take a common factor of 2x. So it looks like this. 2x times 1 minus lambda. If I bring everything to the left-hand side on the second equation, what I get is 2y 2 minus lambda is equal to 0. And I should not forget that they still have to satisfy, they have to be points on that circle. So now, first, it could be, so there's some cases. It could be that for this to be 0, either x is 0 or lambda is 1. So what happens if x is 0? Well, if x is 0, plugging here, y is plus or minus 1. That could be. Or this equation also, if y is 0, this vanishes. So maybe y is 0. By the way, for this equation to be true, that would mean that lambda is equal to 2. So this is the case of lambda is 2. Now from here, y could be 0. If y is 0, then from the equation of the curve, we get that x would have to be plus or minus 1. And for this equation to be true, can it be true? Yes, if lambda is 1. That's okay. So it could be that. Okay. Or I could have, let's see what happens if lambda is 1. If lambda is 1, then that makes this 0. But then if I plug lambda in here, what I get is 2y is equal to 0. That tells me that y is 0. And I get to the same conclusion that x is plus or minus 1. Or if lambda is 2 in this equation, then if you plug it in here, what I get is that minus 2x is 0. And that tells me that x is 0. And then I get that y is plus or minus 1. And this analyzes all the possibilities for all three equations to be true at the same time. There's always more ways. There's no just one way of solving these equations. But all I got is that there's two possibilities. Either I have 0 plus minus 1 or plus minus 1, 0 are all the points where there might be local max or there will be the max or the min has to happen at those points. Okay? And then you just evaluate. So I got, so the candidates, I'll come back to that slide in a moment, but the candidates are 0 plus minus 1 and plus minus 1, 0. And that gives me f at 0 plus minus 1 is, if I evaluate, this is just 2, while f of plus minus 1, 0 is just 1. So 1 is the max, 1 is the min. So this is the maximum value, and it tells you where it happens. And this is the minimum value, and it tells you where it happens. So the maximum happens at 0 plus minus 1, and the minimum happens at plus minus 1, 0. It has to be parallel. We want parallel so that the two vectors are parallel. So I've reached the point where I cannot grow any more on that curve. So they have to be that the perpendicular vector to the curve and the perpendicular vector to the level curve are parallel. So any growth would be outside of the curve G. We can talk. All right, everyone.